Throughout my description of the kinematics of simple harmonic motion thus far, I was always starting the clock when the oscillator was at a specific point in its oscillation. That is, at times t is equal to 0, the position of the oscillator was equal to positive A, the amplitude, in other words, on the right-hand side of the equilibrium position. How do I mathematically account for starting the clock at any arbitrary point in the oscillation? So, for example, as the oscillation occurs, let's say that I start the clock right now, like so. How do I then describe the position, velocity, and acceleration of the oscillator when I start the clock at an arbitrary point in the oscillation? In order to do so mathematically, that is, mathematically account for this, what we do is we introduce an extra term called a phase angle into the argument of the trigonometric terms of position, velocity, and acceleration. This extra term, called a phase angle, shifts the graphs from one side of the graph to the other to mathematically account for ultimately starting the clock at an arbitrary point in the oscillation. What I'm going to do in this lecture is develop a shortcut for quickly graphing out these phase shifts, as they're called, when you have a phase angle in the argument of these trigonometric functions. And then in order to come up with that shortcut, it ultimately comes, as you'll see, from the employment of trigonometric identities. So let me go ahead and move my phone. Like so. Let me tilt it up. Like so. Okay, so mathematically, accounting for starting the clock at an arbitrary point in the oscillation. Okay, here's what we do first of all in the position function. What we do is we introduce an extra term, this constant phase angle phi, as it's called in the argument here of the position function. This then corresponds to what is called a phase shift on the position graph. As I've said, in this video, I'll develop for us a shortcut for quickly graphing out this function by using a phase shift. Now, the velocity function and the acceleration function also have this extra term incorporated into them. In terms of derivatives, because this term is a constant, it basically just gets dragged along in the process of finding velocity as a function of time, which is this expression here, and then lastly, acceleration as a function of time. Now, the easiest way for me to develop this shortcut that I've been alluding to is to immediately take a look at a numerical example. It's going to be the same function as the previous video. I'm just going to change it up a little bit. So let's go ahead and access it here. Please write it down into your notes. Okay, an SHO has the following position function. Let me go ahead and write this down. That is like so. Given this. So notice that this function is very similar to that of the previous example. In fact, a number of the quantities are the same. For example, the amplitude is still 3 meters. The angular frequency, omega, is still pi over 4 radians per second. And then therefore the period, capital T, is still 8 seconds. And now I have this phase angle here, this pi over 2. This mathematically accounts for starting the clock at a different point in the oscillation. What we're asked to do in this problem is to graph the position as a function of time and use a trigonometric identity to quickly develop a shortcut for graphing phase shifts. Now, let's say that I don't know anything at all about shortcuts. How am I going to graph out this function? Well, I chose the pi over 2 here as the phase angle for a reason, because through a trigonometric identity, this then simplifies the expression considerably. So let's approach this then by using specifically the subtraction identity for cosine. So now let's go ahead and use that trig identity. Let me write that here. And so then therefore the position is now the following. I'll put it here in brackets. We take the cosine of the first angle, times the cosine of the second angle, and then there's a sign switch for the cosine identities, so plus sine of the first angle, and then times sine of the second, like so. And now here in the brackets, as I've said, I chose the pi over 2 for a reason. Here in the brackets, now the function simplifies considerably. So in the first term, we have right here cosine of pi over 2, which is 0, and then the second term, sine of pi over 2, which is 1. So if you then simplify what's left over, you end up with this. So notice through a trigonometric identity that kind of in disguise, if you will, this rather complicated cosine function is actually nothing more than a sine function. And of course, we can graph that from basic trigonometry. So let me go ahead and graph out this sine function. Like so. Okay, so we have time in seconds, we have position in terms of meters, and now using a different color, right here is a sine function for a full oscillation, so then therefore this time right here is the period of 8 seconds. Here and here are the amplitude positions of 3 and -3 respectively. Okay, now where is the shortcut in all of this that I'm describing? Well, the shortcut is as follows. Okay, what I'm going to draw here is just a cosine curve. So here's a cosine curve like so, and for this particular example, I'm actually also going to extend it out here to the left, like this. And now notice the following. Notice, for example, that if I take this point right here on this cosine curve, and I shift that point along with the entire curve to the right-hand side, that is like so, until it lies here on the vertical axis. If I shift this purple cosine curve in this manner, notice that I end up then with the sine function that I graphed. Now, how much in terms of angle did I shift this cosine curve by? Well, this right here is one full oscillation, so that's 2 pi radians. Halfway would be pi radians. This right here is 1/4 of the way, which would be pi over 2 radians. So if I take this cosine curve and I shift it to the right by pi over 2 radians, then I end up with this sine function. That's the shortcut. Here's how you read the shortcut in the original function. The negative sign here in the argument of the cosine, the negative sign that is in front of the phase angle, that tells us to shift the curve to the right. If it was a plus sign, through trigonometric identities, we would find that instead it shifts to the left. But a negative sign means shift right. And then the amount that we shift by is the phase angle pi over 2 itself. So we shift by this amount. That's how you use the shortcut. Once you understand how the shortcut works and you understand that it comes from trigonometric identities, then you don't have to bother doing the trigonometric identities anymore. You could just go ahead and directly use the shortcut itself. So that's what I'll do in my next video. In my next video, I'll do kind of like what I call a full-blown kinematics example, if you will, for simple harmonic motion that takes into account everything that we've seen thus far.